Okay, we're going to write an algorithm that is going to reverse every k nodes in a linked list. So if k were equal to 3, then our output would be 3, 2, 1, 6, 5, 4. So in order to do this, we're going to do a standard linked list reversal k times, and then we'll recurse through and do it again for each grouping of k. So let's go ahead and define our nodes. We've got, can make them generic. We've got, no, that is not what I meant to do. Node T, I mean T data, and node next. And then we've got our linked list. And it has the head in it. Okay, so let's go ahead and start our function. It's going to take a node. We'll just say it's an int. And then it's going to first, and it will take in our head and k. Okay, so what we want to do is we're going to need a previous pointer. We'll start that out at null. We're going to need a next pointer. And we're going to need a current, and that's going to equal the head. Okay, so as we go through this, we've got current, next, and previous are both null. Okay, so then what we're going to do is, oh, we also need a counter to keep track of k. We'll start that at 0. And then we go while count is less than k. And current does not equal and current does not equal null, then we can go through and we'll set next equal to current dot next. So now next is here. And then current dot next is equal to previous. So that would put it, just to say previous, and previous is null right now. So actually I'm going to say null instead, just so we can stay organized. And then previous will equal current. So now previous is here. And current equals next. So current is now here. And then we count plus plus. Okay. And then if there's stuff in the new that we haven't processed yet, so if next does not equal null, then we want to recurse, and we're going to store the result in heads next, so that ultimately, like right now, our head will change. If we have k equals 3, our head would change at node number 3. And it would be, we would want to make sure its next is pointing to, at the very end, it will be pointing to the 6. So we want to make sure that we capture that. So if we say head.next equals reverse, next is going to become the new head. We still have k. And then after that, we can return the previous, because the previous will end on the theoretical new head each time. So let's go ahead and see if this is going to work. Let's go. I'm going to make it here so it's easier to read. Make a little. So we have 1, 2, 3, 4, 5, and 6. This is null. This is our head. Okay. So we have previous is null. So we can just say we have previous and it's null. And next is null. And then current is head. And then count is 0. So we'll just keep track of count over here. All right, so while count is less than k, and k we're going to set equal to 3. And current is not equal to null, which it's not, then we can go in. Next equals current dot next. So next is here. Current dot next equals previous. So this is going to point to, right now it's going to be null because previous is null. And previous equals current. Okay. And current equals next. So current comes here. And count plus plus. Okay, so 1 is less than 3, and current is not null, so next equals current dot next. So we move next here. Current dot next equals previous. Okay, previous equals current. Okay. Current equals next. And count plus plus. The count's 2. 2 is less than 3. And current is not null. So next equals current dot next. Current dot next equals previous. Previous equals current. And current equals next. Count plus plus, count is now 3. 3 is not less than 3, so we get out of our while loop. If next does not equal null, which it does not because it's pointing at this 4 node, then head.next is going to equal, and we're going to go through our recursion. So we go in and reverse, and so now next is going to be sent this one and k, which is 3. So we go in and previous equals null. Okay, so previous is null. Next equals null. Next is also null. And then previous equals, or sorry, then current equals head, which it does. So we have current. Okay, and count is 0. So while count is less than k, which it is, 0 is less than 3, and current does not equal null, which it does not, next dot current equal, or next equals next dot current, or current dot next. So next is here. Current dot next equals previous. So we're here. Oh no, sorry. We're at null. Previous is null. And then previous equals current. Okay, then current equals next. Count plus plus. Okay, so then we've got count is less than k, and that's true. And current is not null. We get next equals current dot next. So this is next. Current dot next equals previous. Previous equals current. Current equals next. Count plus plus. Count is now 2. 2 is less than k, and we are still at current not equal to null. So next equals current dot next. Current dot next equals previous. Previous equals current. Current equals next. Count plus plus. Okay, so now 3 is not less than 3, and coincidentally current is null. So we fail our while loop, we get out of that. If next is not equal to null, which is false as well, because next is equal to null, then it says return previous. So we're returning this node here, the 6, and it's going back into the previous function. So head.next is going to equal 6. So that's going to mean that here's our head, still over here at 1. And it's going to, instead of being null, going to go all the way here and point to this 6. So if we look at, and then that was the last function. So then technically it's going to return this head node, the new head, outside of the function as well. So that's perfect. Let's make sure this all looks okay. So what do we have here? We have 3 points to 2. 2 is next with 1. 1 goes to 6. And then 6 goes to 5. And 5 goes to 4. Okay. Oh, and actually the return previous will be the 3 on this final thing, because when we were in this previous function, our previous was right here when we were in our first call to reverse. So when it did the recursion, it went back to the state it was in. So that'll be perfect because it's going to return previous, which is our new head. And 4 was pointing to null. So that works out. And this is an O of N time complexity, and it uses no additional space.